Hello, in this video we will be looking at section 9.6 where we focus on the chain rule, and we will also look at how some of the examples fit into a more generalized version of the power rule. So first of all, the chain rule is going to deal with composite functions. We're going to begin just by reviewing what composite functions are, and then once we kind of have that algebra review done, then we'll actually get into it. So, as a reminder, if you are looking at notation that looks like this, g composed with f of x, another way of reading that would be g of f, that's defined to be g of f of x. Or if we switch the roles of, or the relationship between f and g, then if f is first, this would be f composed with g of x, would be the same thing as saying f of g of x. One thing we can do with functions is we can try to decompose them. So in this example we're looking at down here, what we see that y is equal to x plus 2 raised up to the 8th power. Now, we can think of this as just being its own function, or we could think of it as being the composition of two functions. So if we wanted to rewrite this, we could think of y as being f of some other function, g of x. Now, in this relationship, g is inside and f is outside, so you'd have to look at y and try to decide, is there some inside part that we could write down? It's like that's g of x. In this case, x plus 2 would be kind of a clear winner. Then we want to think, is there some outside part, some outer f function? In this example, you have something is being raised up to the 8th power, so then we'll just write that as being x to the 8th is the outside structure. So again, the inside was x plus 2, inside is x plus 2. The outside part is we had something raised up to the 8th, so something is being raised up to the 8th. Now, how could we check to see if this is the correct composition? We could ask, what is f composed with g of x? This is equal to f of g of x. So then f was x to the 8th, and if you put, this notation just says put the entire g function into f, so we're going to put the entire g function into f. So what we would see is we get x plus 2 is the inside part, being raised up to the 8th. And then this is what the original function was. So we have correctly decomposed that original function into kind of two component functions. If we look at the next example, you have an inside function of x squared plus 3x plus 7. So let's go ahead and write that down. X squared plus 3x plus 7. And then we have the outside function, and the outer part of the function is just the square root of something. So I'm going to write the square root of something. Right? Again, we're thinking y needs to be f composed with g of x, or another way of saying that is f of g of x. So we can check this. What happens if I actually compose these two back together? F of g of x is equal to f of g of x. So what we get is we start with the f function as the square root of something. Then you have to, anytime when you're writing f, you have to replace the x value with the entire g function, because the entire g function is inside of f. So all of this goes in place of that x value, and then we have x squared plus 3x plus 7. Okay, now the reason this is important to be able to do this type of stuff is because when we think about this chain rule, it's going to rely on being able to think of an inside function and an outside function and computing derivatives of both of those. But let's go ahead and look at what the whole chain rule looks like. All right, it says, suppose that you're looking at some large function that's actually the composition of two smaller functions. So f and g are going to be differentiable functions, and you're trying to figure out the derivative of y, which is the composition of the two functions. y is actually going to be differentiable, and the way we compute its derivative is like this. So what we do is we compute the derivative of the outside function. You put the inside function into it, but you leave it alone initially, and then afterwards we are going to multiply by the derivative of the inside function. Okay, that is a lot of me saying inside and outside. I think it might be more clear if we look at an example. Here we have y is equal to 2x plus 3, and all of that is being raised to the second. I would like us to compute the derivative in 3 different ways. First, we will expand it, then we're going to use the product rule, then we're going to use the chain rule. Now, I guess I won't necessarily do them in that order. Let me start with the chain rule. So for the chain rule, what it says is we think about the inside function and the outside function. So the outside function in this case would be x squared, and the inside function would be 2x plus 3. You have to also think about what the derivatives of both of those functions are. So f prime is going to be equal to just the derivative of f, so that'll be 2x. And then you think about g prime, and the derivative of g is going to be 2. So what the chain rule says that we do, just kind of following through this here, you start by writing the derivative of the outside function. So you look at this and you're like, okay, I'm going to have y prime is equal to 2x. So you're thinking about the derivative of the outside. 2 comes out in front, and then the 2 gets reduced to be a 1, so the derivative was just 2x, so it's 2 times something. You don't really have to show this one. In fact, I normally don't, but if you want to see it, it's there. Okay, then what the rule says is after you've taken the derivative of the outside, what is inside should remain unaltered. So we look back at this, and we're just going to write 2x plus 3 in this blank. This is 2x plus 3. I have not changed anything at all about it. But we are not done here. You can't just take the derivative of the outside. The inside, you also have to think about its derivative. And the chain rule says you just multiply by the derivative of the inside at the very end. So we go ahead and do that. We are multiplying by the derivative of the inside, which in this case is just 2. Now, this is the answer. We will simplify it, right? Because this exponent of 1 doesn't mean anything. In fact, I'm just going to erase it. We can simplify this by multiplying these two 2's together. 2 times 2 is 4. Then that's outside of parentheses, so we'll go ahead and distribute it into parentheses. 4 times 2 is 8. That's 8x, and then 4 times 3 is 12. So 8x plus 12 ends up being our answer here. All right, so we've computed the derivative using the chain rule. Next, let's go ahead and use the I'll just go back to the beginning. Let's expand the function out and then take its derivative. So if we had wanted to compute it using this method, you would write 2x plus 3 times 2x plus 3, and then you would have to multiply it out. So this is what y is equal to. If we FOIL this, we get 4x squared plus 6x plus 6x plus 9. So y is equal to 4x squared plus 12x plus 9. And then you could compute y prime because it's all simplified now. So y prime is 8x plus 12, and then we're done. Okay, let me box all of my answers in. Now, that's definitely going to feel the easiest in this example, but when we look at future examples, if you even scan down to the bottom of the page, there's not a chance at all that I would want to multiply this expression out 8 times to find its derivative. The chain rule really is superior to this strategy of expanding in everything except for the very basic cases that we just are looking at right now. Okay, let's also do this using the product rule, right? So this is a nice reminder about what the product rule is. The way I've been doing it in our notes, we have u and v. Now, technically, if just looking back to what we wrote over on the left, this first one is u, the second one is v. So u is equal to 2x plus 3, v is equal to 2x plus 3. Then we compute u prime and v prime. U prime is 2, v prime is 2. And then we multiply along the diagonal. And what we get is that y prime is equal to, okay, on that first diagonal, you got 2 times 2x plus 3, and then you add on the second diagonal, you have 2 times 2x plus 3. So when we distribute this out, we have 4x plus 6 plus 4x plus 6, and then we get 8x plus 12. So all three methods give us the same derivative, which is kind of fun. But in more involved examples, the expanding method and the product rule method, they're just not feasible, like the example you see down here at the bottom of the page. So let's look at that. How would you compute this derivative? Well, one method, which is a terrible method, is let's write it out 8 times. Like, so you have 8 things in a row, and then we're going to FOIL all of that together, and that would take up like more room than we have. So let's not do that. The efficient method is we're going to use the chain rule. So let me switch over to red, because apparently that's what I'm using for the chain rule on this page. What the chain rule says is it says we start the derivative by computing f prime. So you're looking at this, and it's not even necessarily helpful to write all of this information down that I did last time. Like, when you look at this, you have an inside part that you ignore, and you have an outside part that you think about its derivative. So what do we normally do to take the derivative if you have 8 as an exponent? Well, normally you take the 8 down in front, and then you reduce it by, the new exponent gets reduced by 1. So 8 minus 1 gives us the new exponent of 7. Now, in previous sections of notes, we just had an x here, but now we have a function instead of a variable. So the chain rule tells us what to do. And what the chain rule says is, at first, you don't do anything, you just leave the function alone, but then afterwards you multiply by its derivative. So I'm looking at 2x squared plus 1, I'm going to write it here. At first, I'm not going to change anything, I'm just going to leave it alone. But then afterwards, I have to multiply by the derivative of the inside part. So you're looking at 2x squared plus 1. What is that derivative? And the derivative of 2x squared would be 4x. And the derivative of 1 is 0. So this is our answer. Now, we would like to simplify it. There's not a lot of simplifying we can do, but you can definitely say that 8 times 4 is 32. And then kind of write this in the following manner. Y prime is equal to 32x times 2x squared plus 1 raised up to the 7th. So this process was very efficient, and it would have been like insanity to write this out 8 times when we have this really easy option. All right, let's just look at some more examples of the power rule. So we want to compute d dx, so the derivative with respect to x, of this following expression. When you look at this expression, the first thing that you should do, I hope that your instinct, is to start by rewriting this. I'm not willing to try to take a derivative with a square root, so what I'm going to do is I'm going to rewrite the square root as a rational exponent. We're taking the derivative of x squared plus 2x minus 7. Now, the square root just becomes the exponent of 1/2, and then I'm taking the derivative of that expression. Okay, now that I've rewritten it, I can apply the chain rule. What the chain rule says is you start by taking the derivative of the outside structure. So whatever's inside initially is just going to be left alone. So this is going to be equal to x squared plus 2x minus 7. We leave it alone, and we only think about the derivative of the outside. So that 1/2 exponent is going to come down in front, and then the new exponent is going to be 1 less than the previous one was. So if we take 1/2 and subtract 1, we should get negative 1/2 as our exponent. Now, it's tempting to stop right here because it felt like, hey, we just took a derivative, but you only took the derivative of this outside structure. The chain rule says to leave the inside alone at first, but remember, anytime you use the chain rule, you have to chain something on. And that's why it gets called the chain rule, because it's like you took one derivative and then you chain on another derivative. All right, so this second derivative is 2x plus 2, and that's it. Now, you can leave your answer like this. Certainly, there's a little bit of simplifying that could happen. You're allowed to multiply this 1/2 coefficient, distribute that into this second set of parentheses because it doesn't have an exponent that's restricting you, but you definitely cannot distribute 1/2 into the first set of parentheses because of the exponent. You also can't try to do any multiplication or foiling. So this is almost our final answer. We're just going to take 1/2, multiply it to both of these. We get 1/2 times 2 is just 1. 1/2 times 2 is just 1. And then we can write x squared plus 2x minus 7 raised up to the negative 1/2. And that's our answer. Nothing we can do beyond that. Now, you may see in some books or examples online that people will rewrite this. You are capable of rewriting this. So technically, a negative exponent means you're dividing by something, and you would be dividing by this thing raised up to the 1/2. But we know that 1/2 really is the same thing as a square root. So you could rewrite this as x plus 1 divided by the square root, and then it's x squared plus 2x minus 7. All right, these things are the same, but this first one is preferable for me for a brief calculus class. So that's it. Let's go ahead and look at the next example. So we're looking at G. Let me erase some of this that got in the way. All right, we want to compute G prime. So you're looking at this, and we can just go for it. G prime of x is equal to, we start looking at these one at a time. What is the derivative of 2x? And we decide it's just 2. Then we're adding on something, no problem. What's the derivative of this? You look at this oh, that's a chain rule. So how do we think about the derivative of something that's being chained? Well, we're going to add on. Initially, we don't mess with the inside. You just leave it alone. And you think about what's the derivative of the outside. The 10 comes down. We reduce the size of the exponent by 1. Is that our whole answer? Absolutely not. You have to chain something on if you're using the chain rule. What do I multiply at the end? What gets chained on? It's always the derivative of what was inside. So you do compute the derivative of what was inside, just not at first, you do it at the end. All right, derivative of x squared minus 1 is 2x. This is my answer. Now I'll simplify it a tiny bit, but I have done all of the calculus at this point in the problem. The only thing we can simplify, though, is 10 could be multiplied to the 2x, and what we're going to get is we're going to get 2 plus 20x times x squared minus 1 raised up to the 9th. Again, because there was this exponent, nothing that's outside could get distributed in, because that exponent of 9 kind of locks it all in together. Next, let's look at an example that we get to think about negative exponents with. How would we compute this derivative? Well, the first thing we would do is we would realize that this is really the same when you're looking at 1 over x plus 2. That's really the same thing as saying x plus 2 was raised up to the negative 1 power. Once you have written it this way, you can think about using the chain rule for this. This derivative is equal to negative 1 x plus 2 raised up to some new exponent. When you think about it clearly, you should get negative 2. Remember that you always take the previous exponent and subtract 1 from it. So negative 1 minus 1 gave us that new exponent. Then you have to multiply by the derivative of the inside function. Now, in this case, you look at the derivative of the inside function, you're like, oh, well, that's just, it's just 1. So multiplying by the derivative in some cases doesn't actually change what that function had started out as. So but it is still a necessary step to show. We want to simplify this a little bit. We're going to call this negative 1 times x plus 2 raised up to the negative 2. That's our answer. In books or online, you may see people write this as negative 1 over x plus 2 squared, and that's also correct. It's fine to think about it that way, to write it that way, but I just won't require my students to reconvert it here at the very end. Okay, last thing we want to look at is this application preview, where we think about like how would the chain rule feel in an application type of a problem. Okay, what we have is we have the demand for x 100 units of production is given by this equation. If you care, and it's not actually important to write this down, but if you care, this could have been written as 98 over the square root of 2p plus 1 with a minus 1 there at the end after the fraction. In some instances, that may be what your homework question looks like, and then you have to first of all convert it into this format that uses a rational exponent. So that's our function. P is the price per unit in dollars, and we want to find the rate of change of the demand with respect to the price. Now, the first thing that's worth just thinking about is when we are asked to find a rate of change, what does that mean? Rate of change always means compute a derivative. So the rate of change of demand would be like, the notation looks a little weird here because it says the demand for x 100 units is x equals this, and then p is the variable. So it's really strange to have a function like start out with an x. You could maybe get away with saying x prime is equal to, but really like a better notation is we are taking a derivative of x with respect to p. This is equal to, and now we just take the derivative. So you're looking at this like, okay, I start with that 98. The coefficient just kind of hangs out in front. Then I'm going to have some parentheses, 2p plus 1. I'm not taking that derivative yet. First of all, I get to think about what should I do with this negative 1/2? Like when you take a derivative, what do we do with that exponent? Well, first of all, it comes out and it multiplies to the number out in front. Now, I'm going to do the multiplication later, which is why I already wrote the 98 down. But negative 1/2 comes out and it should get multiplied to the number that was already out there. Then the new exponent is going to be the previous one minus 1. So this would be negative 3/2 because we had negative 1/2 minus 1. Then we continue on, and it's easy to lose track of this step, but after you have taken the derivative of the outside, you must always tack on the derivative of the inside. So then we multiply by the derivative of the inside part, which in this case is 2. That takes care of everything up through here. You still technically have to think about the derivative of the minus 1, and you realize that would just be 0. So as a technicality, you would have plus 0 at the end. I'm not even going to write it, but we thought about it. Yep, the derivative of a constant is just 0. Okay, so now we're looking at this. We want to simplify it. We have 98 times negative 1/2 times 2. 1/2 times 2 is going to become 0. Or if you've already taken half of 98, then you can just double it to get back to 98. But this will be negative 98 times 2p plus 1 raised up to the negative 3/2. And that is our derivative. So this is the derivative of x with respect to p. I boxed it in without thinking. Let's go read what the question is asking. Find the rate of change of the demand with respect to price when p is equal to 24. Okay, so then let's go ahead and write that notation. The derivative of x with respect to p evaluated at, it says when p equals 24, we'll just say p equals 24 as our notation here. So if you haven't seen this notation recently, all this means is you're going to plug 24 into the derivative function. So here's the function you're thinking about. This is the number you're plugging in. So here's the function. You're plugging 24 into that. Go ahead and do that in a calculator, and what you should get is this. You should get a decimal that is equivalent to -2/7, but the approximation would be -0.2857. If you are not getting this number in your calculator, just make sure to put parentheses around that exponents. So what I actually typed in would be this. Just multiplying the coefficient to 49, then we raise it up to and we put parentheses around 3 divided by 2. Since this does work out to be like -1.5, you could just say 49 raised up to the -1.5, and that would also remove the need for parentheses. All right, one more example, and then we're out of room. So, actually, let's just go up here, and if we need to, we'll go into the empty space. So let's compute y is equal to, let's compute the derivative of y, which is equal to 3x plus 11. Quantity is raised up to the third power and is being multiplied to the square root of 4x minus 2. So you look at this, and when you start thinking about this, you're going to notice a couple of things. And first of all, what you should notice is this looks like a product rule problem. You have one function times another function. So you could think of the first one as u, the second one as v. I'm going to start structuring myself this way. U is equal to something. 3x plus 11. That's all raised up to the third. And then v is equal to the square root of 4x minus 2. But instead of writing the square root, I'm just going to convert the square root to be the exponent of 1/2, because I'll need to think about it that way when I go to compute its derivative. All right, so from the beginning, we looked at this. It's one function times another function. Got to use the product rule. So we start by thinking about it in terms of a product rule. But when we go to compute the derivatives of u and v, you're going to have to use the chain rule as part of that process. It's not hard, but it's just something like an extra layer that you have to think about. Okay, so what is the derivative of u? Well, you would put the 3 out in front. You would then multiply 3x plus 11. You put the exponent of 3 out in front. Then you reduce the exponent by 2. Then afterwards, you have to multiply by the derivative of the inside function. So you look at this inside function, the derivative of 3x is 3, so we get another 3 in this example. I'll simplify that to 9 times 3x plus 11. That quantity is being squared. Then we compute v prime. V prime, we take the derivative of the outside, that's 1/2, 4x minus 2, and then we raise it to the exponent of -1/2. Now, you have to tack on the derivative of the inside. So the derivative of the inside is 4, so we're going to tack on a 4 to the end. And we do want to simplify this as well. So I preemptively drew my box, which maybe I should not have done. Boop. Let's get rid of as much of that as I can, and then let's write this down. So v prime is equal to, I'm going to multiply 1/2 times 4 to get 2, then that will give me 4x minus 2 raised up to the -1/2 as the rest of my v prime function. All right, now that was a lot of thinking already, but we took the derivative of u, we took the derivative of v, now we're back to thinking about the product rule. How do we think about the derivative of the product rule? Well, you multiply along one diagonal, and then add that to what you get when you multiply along the other diagonal. Okay, so y prime is equal to, I'll start in the top left. We go 3x plus 11 raised up to the third. That has to be multiplied by 2 times 4x minus 2 raised up to the -1/2. Okay, if all of these parentheses are obnoxious to you, you can always migrate that 2 to just be out in front, and then you don't have to have this set of parentheses here. But it's fine like this. And then we add on I'm going to multiply along the other diagonal. This time I'm going to start in the lower left. So 9 times 3x plus 11 squared. And then I multiply it to the top right. So that's 4x minus 2 raised up to the negative 1/2. All right, now this is our answer. Please don't try to simplify this. It's not necessarily simplifiable. We could maybe do a little bit, but I'm not going to ask you to do anything with this. It looks complicated, but every step on the way was really not. You said, hey, that's one function times another. So we have u and we have v. What's the derivative of u? Well, you have to apply a chain rule. So you think about the chain rule, and you chained on a derivative at the end. What's the derivative of v? This time there was a square root to think about. Okay, but we know that square root is just the 1/2 exponent. When we think about that derivative, we don't forget to chain. And then once you have both of your derivatives, then we just complete the product rule by multiplying along those diagonals. And that finishes this section of notes, so hopefully you find this helpful.